So
Yes.
first of all, thank you for the nice introduction. And above all, thank you very much for this invitation, which I appreciated very much. I think this conference is exciting. It's for you, it's a long week. And I think it is very interesting that you are also confronting the views and perspective of students, guest speakers, teachers. I am really excited by the discussion that will follow. And I also would like to tell you that, to anticipate to you that my presentation is available on my website already now. You can find it there. Okay, first of all, let me introduce briefly my research activity, which is focused on assessment and adaptation to change in the widest sense, climate change, hydrological change, and the purpose ultimately is, as you said, Helen, to give a contribution to mitigate the risk associated to natural hazards in the presence of change, several reasons of change. And in particular, I'm focusing on drought risk assessment. I'm focusing on floods, and in particular on the impact of climate change on floods. And I am also trying to take advantage from advanced monitoring technique. And here you can see an example. This is a nightlight image of the Nile River Delta. We use this nightlight data to estimate the exposure of people to floods. Of course, where there is light, there are people. And along the river, of course, the more the light and the more the people exposed to the flood. And I am also focusing on studying methods for projecting the future climate. And this is the last topic that you see here. It's presented here in technical terms. What it means, stochastic physically based modeling, means producing scenarios for future climate. The whole of my research activity is framed, as you can understand, into the topic of sustainability and resilience. And what I would like to emphasize is that I am firmly convinced, and of course I'm not the only one, I'm firmly convinced that sustainability must be supported by a truly transdisciplinary approach. And I want to be clearer in that by clarifying the differences between multidisciplinarity, where we simply add the knowledge from different disciplines, interdisciplinarity, which is a step forward because different disciplines are combined to a new level of integration, and finally transdisciplinarity, which is the concept that I really like because it means that two or more disciplines are bridged to form a new approach. And I think that really sustainability means that we have to eliminate the boundaries between disciplines and form new disciplines. This is really difficult because change is always difficult. Now, I would like in particular to focus during this talk on droughts, because this is my most recent research topic. And droughts, as you know, are a temporary situation when water resources availability is lower with respect to water demands. And typically, when we think of a drought, we think at a duration of one season. But actually, what we realized very recently is that the real risk, the highest risk, comes when these droughts have a long duration. And we recently experienced in several parts of the world droughts that lasted for several years. I want to give you some examples. The first is the drought of Cape Town, you see here in this slide, which lasted from 2015 to 2018. And it had a very severe impact on water supply to the city. They had to adopt very strict restrictions to water supply. Another relevant example is the drought of California from 2011 to 2017. Again, a very massive impact on the environment, on society. And also this drought lasted several years and then disappeared and then ceased. Another relevant example, the Millennium Drought in Australia, and it lasted for almost 10 years. And also what was really surprising in this drought is that the deficit in precipitation during the period, which is minus 11%, was amplified in the river discharge, which was reduced during this period of about 50%. And the reason of this amplification are not fully known. At the same time, we don't really understand what are the reasons inducing these multi-year droughts. Is it climate change? Is it global warming? Is it some other anthropogenic influence? This is something that we need to understand better, and it's extremely important because in the recent decades, as you have seen, we knew that our modern water supply systems cannot cope with these multi-year droughts. Now I would like to refer to my region, the Emilia-Romagna region. What you see on the left here, this is the series of the annual minima of the Po River. Along the Po River in several stations, we have daily measurements of the river discharge. And the series that you see on the left is the series of the lowest discharge in the lowest day of the year. And you can see that if you draw a regression line, there is a declining trend. So one may think that this is a tendency that is persistent. But if you look on the right, you see the same series where the regression line is estimated on a moving window, which is 50 years long. And you see from this right figure that at the beginning of the period, you have a declining trend, but at the end of the period, the trend is reverted. So actually, it looks like there are cycles in these climatic variables which we don't fully understand. Another useful example for my region is this figure on the left. This is the annual rainfall in Bologna from 1813 to today. This is a very interesting series because it's very long. We have daily observations. What you see in the graph is the annual total. And what we can see here in gray is the occurrence of multi-year droughts. And again, you see that this event is quite likely. It was even more likely in the past than recently. And this is something that if it occurred today, it would be really a disaster. An event like this one, which you see at the beginning of the 18th century, if it occurred today, it would be a disaster because our modern water supply system cannot cope with this multi-year deficit of water. So how can we study these phenomena? How can we understand better? There is an obvious solution. A very interesting solution is to use climate models. To use climate models in order to understand what are the causes of these multi-year droughts. And in terms of climate simulation, I think there is a very interesting opportunity that is offered by the Copernicus Climate Data Store. This is freely accessible. You just need registration. It's an outstanding source of information because simulations are available and for historical data. Also, historical data are available there, and you can get climate projections for the future. And also, it's very efficient to retrieve data from there. You need some programming skills. It's not very easy, but at the end, the process is very efficient. And what I did here is to get the projection of the annual rainfall in Bologna, because I wanted to try to understand whether from now to 2100, we can expect similar multi-year droughts, similar phenomena. And so I got the simulated series, which you can see here on the right. This is the series of the daily data. And here you can see a comparison between the historical series on the left, this is the historical one, and the projection on the right. Actually, what came out is something that confirms in a way what I was expecting, and in particular that the output of climate models in terms of hydrological variables like rainfall, it's not very useful for studying the occurrence of multi-year droughts, because as you can see, the statistical behavior of the two series, even by eyes, look quite different. And if we look at some statistics, you see that on the left, you have the statistics for the historical series, on the right, the statistics for the simulated series. And you see that there are differences in the mean value and in other statistics. There are also differences in what is called here intensity of long memory. What is this? It is an indicator of the likelihood of long-term cycles. It's an indicator of the likelihood of droughts. And what you can see is that the two numbers are different, meaning that while the historical series says that droughts are likely, the simulated one doesn't say the same. It says that they are less likely. So basically, also, if you make a comparison between observed and simulated data, keep in mind that climate models are not conceived to reproduce observed data. So this comparison, it's really not very significant, but I'm just showing it to demonstrate that if you make a comparison of for the period where we have the overlap of observed and simulated data, there is uncertainty. What you see here in the bottom is the progress of the mean monthly rainfall. You see that there are differences. So what is the conclusion? The conclusion is that we cannot just rely on the output of climate model. We need something more. And this is something that we are very interested in engineering, because in engineering, we need to make design. We need to rely on something that also is prone to uncertainty assessment. So what can be a possible solution for using the information given by climate models, which is very important, but translating this information in something that is useful to technical design? And what I would like to discuss now is the so-called bottom-up approach. It is a typical approach in water resources management. And the bottom-up approach starts from the risk assessment in current condition. So did we experience some droughts in the past? Are we aware that our systems, I'm talking about water now, are not enough resilient, are not resilient enough? Okay, so let's estimate what we need now in order to solve the current problems. So let's start from the current problems, not from projections. In this way, we are sure that we identify no regret solution. And then we come to design of solution to solve the current problem. And then we take into account future climate scenario to assess resilience of our solution. And let me say that these scenarios must be the term that I use, technical, meaning that they have to be reliable to support technical design. If we have additional information, we can use it. And the end of the story, at the end of our bottom-up approach, at the top, we get no regret solutions because we started from no regret solution and resilient solutions. It's called bottom-up because it's the counterpart of the top-down approach, which is a classic approach in climate impact assessment that starts from the projections of future climate. Here, the proposal is to start from the analysis of the current situation. Now, I talked about technical scenarios. What do they mean? Basically, we need scenarios that should take into account the information that comes from climate model in a useful way for design. So we need for design uncertainty assessment. We need good performances in the simulation of the current climate. So we need to overcome the problem that I introduced to you when I compared historical rainfall in Bologna with the projected rainfall. We need to overcome this problem. We need to make an efficient use of the available information. And of course, our approach must be target-oriented, like any approach in engineering. So what is the proposed approach? It's a mix between using climate models is integration between climate models and statistical models. Statistical models are based on the use of historical information. So they take advantage of the historical data, and they are mixed in a transdisciplinary framework with climate models. It is an hybrid model. The term hybrid is very popular nowadays. And I like to call it an hybrid approach, which puts together climate science and statistics and engineering. And so let me just give you, I don't want to give too many details because it becomes too technical, but I just want to give a couple of references. This approach was proposed some years ago. It's a statistical approach because it must lead also to uncertainty assessment. So statistics also provides the means to give you uncertainty of the design. And what is innovative is the incorporation of the output from climate models. So how is this possible? And let me give you an additional slides with just a few more details. So first of all, as I said, we start from the historical information and we build a statistical model. And the statistical model is used to make a simulation. And then I take a climate model. I select the variable of interest, which may be an hydrological variable or maybe temperature. And then once it is selected, I use the climate model. I integrate the climate model in the statistical model. How to do this? It becomes too technical. I am available to give you additional details if you wish, maybe later on. You are welcome to contact me later on. At the end of the story, we end up with design variables that can be used in engineering. I want to give you an example of application. This is not related to me. I just came across this paper, and these persons these researchers, and you see the paper here and the authors in Australia, what they did is to use temperature generated by climate models to condition their statistical simulation model. So they didn't use directly the variable from climate model, which is more relevant. They used the more reliable. It is well known that climate models in simulating future temperature are more reliable than in simulating hydrological variables. So the idea here is to make this integration and look at a conclusion in the abstract. This approach is practical as it takes advantage from the fact that climate model projection for temperature change are more realistic than climate model projections for rainfall. Now, I am now going towards my conclusions, but before I conclude, I would like to show you a couple of slides that summarize also my experience in teaching. And I wanted to start with a premise on the need after COVID-19 to adopt a very positive view. And I think COVID-19 was a disaster. The details, we know the details very well, but at the same time, it gave us some opportunities. And in my university, we have been discussing whether we should adopt some kind of streaming for making our lectures more accessible to students. We have been discussing for years, at least 10 years. And after COVID, we were able to equip our lecture rooms with the technology to go in streaming in a couple of weeks. And now we think that lecturing in streaming, in both physical presence and streaming, will be our future. So I think that we should stimulate this innovation in the framework of transdisciplinarity. You already know that I'm very enthusiastic about this concept. Openness and inclusivity. These three concepts are very related because all of them means that we have to remove boundaries. Remove boundaries, I think it is a overarching concept. If we remove boundaries between disciplines, it will be easier to remove boundaries to data, software, publications. It will be easier to remove boundaries between people. And basically, what I would like to insist is to pursue, to support open data, open software, open science. Everything should be accessible to everybody, because, as I said, boundaries, elimination of boundaries is the key to inclusivity. It is difficult. Crossing boundaries in research activity is very difficult. Why? Because currently we have an academic system for recognizing the contribution, the individual contribution, that it's not supportive of transdisciplinarity. We need to make a radical change of our system for recognizing academic contribution. In education, it's easier because you know, it's we have less constraints with respect to research. And the question I would like to ask you, did you ever try to interact with or teach to students in different disciplines? If you try, you may discover a new world. You may experience excitingly diverse views. And this is the essence of my experience. I started a couple of years ago to teach to several students of different disciplines, and really I discovered a new world. And another pillar is open teaching. I started in 2012 to upload the video of my lectures on YouTube. I started in the same years to publish my lectures on my website, which is accessible to everybody. And I think open teaching is really the key for the future, and it's a suggestion that I really would like to give to you. And this requires, keep in mind, it is an obvious concept. Openness requires very good programming skills. So here you see some terms like Unix, Linux, OS2, MATLAB, Python, R project. If these terms are not familiar to you, now it's time to get familiar with them. My conclusions. First of all, drawing conclusion of a talk is the most difficult part of preparing a presentation. And I wanted to start with this, and also very practical suggestion. It's ironic. I hope it's a kind of joke. Don't underestimate the importance of your last slide, because probably it will remain on the screen during the discussion time. So be careful of that. And some personal suggestions for research and teaching. I leave them to you to read, because I want to save some time as I run about a few minutes late. Thank you very much for the invitation and for your attendance. And I'm really looking forward to any question you may have during the